Classification of monosaccharides is going to be the topic. This first lesson in a chapter on carbohydrates. Now, I didn't originally cover this as part of my normal organic chemistry curriculum. That's for one simple reason. We didn't cover it at the university I long taught at. So, but you guys can thank Sophia. She asked me to cover this. It's part of her curriculum. So if you're overwhelmed with gratitude and need somewhere to express it, you can say thank you, Sophia, in the comment section. All right, so let's start off talking about carbohydrates. Now, they call these carbohydrates. We'll start there, simply because they follow this typical formula here. So for every carbon, there's the equivalent of a water molecule in the structure. Now, it doesn't actually look like that in the structure, so that's where it comes from. So right here, we've got a form of glucose here, and you count it up, you'll see that this is C6H12O6. This is fructose, so find out it actually has the same formula. They are isomers of each other. So and if you kind of break that up, you could say that this is the equivalent of C6H2O6. It kind of follows that carbohydrate formula. So notice it doesn't really look like that and stuff. So one thing you should note that we're using Fischer projections. They're really common in sugar chemistry. And if you need a reminder, we covered those back in chapter 5 and lesson 5.4. So, but quick reminder is that the horizontal bonds are wedge bonds, and the vertical ones around any chiral center are going to be dashed bonds on a Fischer projection. All right, so one thing you should know about these carbohydrates. So we're going to talk about monosaccharides first. So these are kind of the sugar monomers, but we'll talk about disaccharides and polysaccharides, which have two or more than two of these monosaccharide monomers and stuff like that. And we'll have the last lesson in the chapter focusing a little more on those. All right, so if you take a look at the structure of a typical monosaccharide here, so they're going to have one carbonyl group. They're either going to be a ketone, as fructose is right here, or they're going to be an aldehyde, as in the case of glucose here. Every single sugar is one or the other. So, and then every carbon that is not the carbonyl, you find out that every other carbon has a hydroxyl group, is an alcohol. So one there, and then there, and there. And you'll find it's pretty common to therefore have the potential to have multiple chiral centers in a lot of sugars. Now we'll find out that you can have as few as 3 carbons, so and then you can just work your way on up from there. So I put a couple of 6 carbon sugars here, another 5 carbon one over here. So a big thing I wanted to see is just a little bit of variety and see again that aldehydes versus ketones, and we'll see that these are part of the classification system we'll get to on the next slide. So as I stated, all monosaccharides are going to either be aldehydes or ketones. So, and you might recognize the name of a sugar, so because it's going to end with an OSE suffix at the end. So glucose, sucrose, lactose, maltose, those are all sugars. And you should know that the aldehyde sugars we call aldoses. So, and then the ketone sugars we call ketoses. So part of our system of classification we're going to do. And so again, every single monosaccharide is either going to be an aldose or a ketose, and you should recognize, does your carbonyl group come at the terminus of the sugar? So then we'll call it an aldose. Does it come not at the terminus? Then we'll call it a ketose. One other thing you should remind yourself about Fischer projections, in a properly drawn Fischer projection, so your carbonyl carbon as far as the sugar, and really it's the most oxidized carbon, but it's going to be the carbonyl for these monosaccharides, should be as high on the Fischer projection as possible. So for an aldose, it's going to be at the very top. For a ketose, it's going to be as close to the top as possible. We'll find out the only ketoses we're going to consider is going to have the carbonyl group at carbon number 2. Turns out we also classify monosaccharides based on the number of carbons they have. So here's one with 7 carbons. We'd call it a heptose. So 6 carbons a hexose, 5 carbons a pentose, 4 carbons a tetrose, and then the smallest version, 3 carbons a triose or a triose, depending on who you talk to. So and then notice these are all also aldoses. They're all aldehydes, and so we can actually combine the two now. So this would be an example of an aldoheptose, an aldohexose, an aldopentose, an aldotetros, an aldotriose. So, and we could have the corresponding version like we saw fructose had 6 carbons and was a keto sugar. And so fructose would be an example of a ketohexose instead. So we can combine those two systems of classification to kind of get a more classified version of what that monosaccharide is. All right, so now we've got to talk about some important stereochemical considerations here involving our monosaccharides. So, and we talked about the chance to have multiple chiral centers. So if we take a look at glucose here, so it turns out we've got 1, 2, 3, 4 carbons that each have 4 different groups. Notice this last one here does not have 4 different groups because it's got 2 identical hydrogens. And then this one's sp2 hybridized, not sp3, so he's not going to have 4 different groups or even 4 groups in general, and definitely not be a chiral center. But here, glucose has 4 different chiral centers. So, and as a result, you might be like, oh, 2 to the 4th power 16. So, and glucose would represent one of 16 possible different stereoisomers. So for an aldo hexose like this guy. All right, so the question is, what does the D and the L stand for? So we might have learned back when we talked about chirality and stuff like that, that we had a lowercase d and a lowercase l, and those refer to dextrorotatory and levorotatory. So, and it referred to the which way certain isomers were going to rotate plane polarized light. Well, it turns out that's where the capital D and the capital L originally derived their meaning, but it was for one very specific sugar. And so it turns out that now we actually have to come up with a new definition for capital D and capital L here, because these are not the same as lowercase d and lowercase l, the dextrorotatory and levorotatory. They're not actually going to necessarily refer to which direction light's going to get rotated for our sugars here when we use this capital D and capital L. What it is going to refer to, so is the chirality of the lowest chiral center on the Fisher projection. It happens to be the highest numbered chiral center on the Fisher projection. We'll see how this works. So if we look at this glucose here, is an aldose again. So there's carbon number 1, if we were numbering the carbons to name it, 3, 4, 5, and 6. And so the chiral center lowest on the diagram is the highest numbered chiral center, carbon number 5 here. So, and you want to find out where's that hydroxyl group. And if that hydroxyl group is on the right, that's what's going to make it a D sugar. And if that hydroxyl group is on the left in the Fisher projection, that's going to be an L sugar. That's the way this is going to work. And that's going to hold true for all the sugars we identify. You're going to go to the lowest chiral center on the diagram, or the highest numbered carbon, if you will. So, and look at where the hydroxyl group is. If it's on the right, it's a D sugar. If it's on the left, it's an L sugar. So right here we've got D-glucose. So for a whole variety of different hexoses, you might have to memorize some of them. So, and again, there's a lot of them out there, but most of you are probably just going to have to memorize the structure of glucose here. And so if you look, you've got an OH and it goes right, left, right for the pattern for the chiral centers. So you might also realize that if you take your right hand, and you could hold your fingers where the OHs go, and you find out that you're flipping yourself off if you hold it up like that and pull this one back and pull these two back and leave that one out. It's really terrible, but it's a great way to remember it. So flip yourself off, I guess. All right, so that is D-glucose, and that's a pattern you might need to remember there. So if you look at L-glucose, a lot of students get confused on the difference between D and L, and they just think, oh, I just need to flip that chiral center at carbon number 5 around. No, the difference between D and L version of a sugar is that they are enantiomers, and you have to invert every single chiral center. So notice, I didn't just flip and invert chiral center at 5 here, but you can see that I did. I flipped the H and the OH, traded them places, and again, 2 groups trading places on a chiral center does indeed get you the inverted chirality. So, but I did it also at carbon 4. Notice mirror image there, and carbon 3, mirror image there, and at carbon 2. So when you got the difference between a D and L sugar, again, you could recognize that if it's D or L just by looking at a single chiral center, but don't think that that's the only thing you need to change to get the corresponding L version or D version of a sugar. If you've got D-glucose, it is the enantiomer with all chiral centers inverted, not just the lowest one on the Fisher projection or the highest numbered one that's going to be inverted. So just want to make sure you've got that straight. So, but that's your difference between D and L. You're definitely going to want to know that difference. We'll refer back to this a couple of times throughout the rest of this particular lesson. Now with sugars, in addition to enantiomers, we've also got to talk about diastereomers. And you might recall the difference. Enantiomers are non-superimposable mirror images, but they're mirror images that are not identical. So whereas diastereomers, they are not mirror images, and they're still not identical. So non-superimposable, non-mirror images. So a couple different ways to remember that. Again, enantiomers are stereoisomers that are mirror images. Diastereomers are stereoisomers that are not mirror images. So a way to kind of look at that as well. So, and typically we learned a nice convenient way to remember this as long as it's involving chiral centers back in chapter 5. So when you've got many chiral centers, if you invert all of them, you're going to get the enantiomer. If you only invert some of them, but not all of them, then the relationship is going to be diastereomers instead. So look at these first two right here. So we can see that this first chiral center has been inverted. OH on the left, H on the right. Now it's OH on the right, H on the left. So, but notice the other three. They are all in exactly the same configuration. And so out of the 4 chiral centers, I've inverted 1, but kept 3 the same. That's the hallmark of diastereomers, where some of the chiral centers are inverted, some of them are the same. So these are not mirror images, but they're not identical either. They're still stereoisomers that are not mirror images, they're diastereomers. Now we get a new special name with sugar chemistry, with carbohydrate chemistry, and that's for stereoisomers, and specifically diastereomers, where they are different at just one chiral center. And that new word is epimers. So epimers is a special type of diastereomers. All epimers are diastereomers, but not all diastereomers are going to be epimers. So epimers are diastereomers that differ at a single chiral center. All right, so we'll look at the ones on the right here. So once again, so we can see that, both these have 6 carbons. They only differ in chirality. And we see that the top 2 are inverted, but the bottom 2 are in exactly the same configuration. So some in the same configuration, some in opposite configurations. These are definitely diastereomers, but because they differ in more than just one chiral center, in this case in 2 chiral centers, we could not call them epimers. They are diastereomers, but not epimers. So definitely should be able to recognize diastereomer relationships between monosaccharides, but you also now a new word, recognize if they're further epimers or not as well. So it turns out that your monosaccharides can cyclize in solution to form cyclic hemiacetals. So a little difficult to see, and we'll draw them here in just a second. But it turns out the cyclic hemiacetals, especially for aldoses, are much more stable than the linear form, the open chain form we might call it. And so, in solution and even in living systems and stuff like that, they are much more likely to exist, especially aldoses again, in the cyclized form. But we'll see that's even true to a certain extent for ketoses like fructose as well. So, but in solution, you're gonna have an equilibrium established here, and we'll find out that when they cyclize, so you might have a couple of different options, or in some cases, many different options depending on the size of ring. But we'll find that 5- and 6-membered rings, due to their low ring strain, especially 6-membered rings, are typically the most stable and typically the only ones we will consider. Now, if they cyclize to form a 6-membered ring as a cyclic hemiacetal, so we'll call that a pyranose, and we'll find out with a 5-membered ring, we'd call it a furanose. All right, so here we've got a couple of different pyranoses, and we'll find out this is alpha-D-glucose. And specifically, we might even call it alpha-D-glucopyranose, whereas this one is called beta-D-glucopyranose. We got to talk about what's this whole alpha and beta thing. Well, before we get there, we just want to talk briefly about, well, how do we convert the open chain form to one of these cyclic forms? How do we draw one versus the other? Because you definitely have to know how to do that. And it is downright terrible that we require that of you. And you'll see why I said downright terrible in just a sec. All right, now you might recall, for a hemiacetal, you're going to have an alcohol attacking an aldehyde. And in this case, that's exactly what is happening here, but we've got many alcohol possibilities to do this. But what we find out is that when it's the alcohol again on carbon number 5 that does this, we'll form a 6-membered ring. Now we're going to form a new bond between the oxygen here and carbon number 1 right here. Let's just number these for the fun of it real quick. And then we're going to have 5 carbons in the ring and then an oxygen. That's why we got 5 carbons in the ring and then an oxygen. And if we number our way around, this is going to be carbon number 1, 2, 3, 4, and 5. Those are the 5 carbons in the ring. And notice the oxygen here, the one in red, is the one in red right here. So it's going to get deprotonated in the end. So along the way of forming that cyclic hemiacetal. All right, and in this case, you can notice that oxygen is between carbon 5, which was already attached to in the open chain form, but now is also attached to carbon 1, and that's why it's between carbons 5 and 1 here. All right, so a couple things we got to note here. So we're going to draw in some of these hydroxyl groups, and it turns out the reason I said this is downright terrible that we require this of you is because that's how you're going to remember that down and right go together. So we call this a Haworth projection here. It's one way of representing the cyclic forms. We can also draw them in chair conformations as well, and we'll see it's very similar. And the reason I say it's downright terrible is if you look on the Fisher projection, the hydroxyl groups that are pointing to the right are going to point down on the Haworth projection. So if we start at carbon 2 here, carbon 2's OH is on the right, and so the OH on carbon 2 is going to point down on that Haworth projection. So that's why I said it's downright terrible that we're going to require this of you. So notice same thing on carbon number 4. Its hydroxyl group's on the right, so it's going to point down on the Haworth projection. But on carbon 3, the hydroxyl group's on the left, and so that one's going to point up instead of down. And then we can obviously draw in the corresponding hydrogens as well. Sometimes we draw these in, sometimes we leave them off. It is totally up to you. Now, if we go to carbon 5, so carbon 5 doesn't have a hydroxyl group anymore. If you notice, that hydroxyl group, again, is the oxygen that's now part of the ring. So it doesn't have a hydroxyl group. But what does carbon 5 have? Well, it has a hydrogen still, and it has the CH2OH group. So now, if we did draw a hydroxyl group, well, it's on the right, so we would have drawn it down. But again, it doesn't have one. So, but in this case, what we're going to do then is draw the CH2OH group. Well, we're not going to draw it on the right because that's where the hydroxyl group would have been. So we're going to draw it up instead. And it turns out if you draw that extra CH2OH group here up, that is going to be the indication that this was a D sugar. Had we drawn this CH2OH group down, that would have reflected actually the mirror image. It would have been an L sugar instead. But when you look at a Haworth projection, if you see that CH2OH group pointing up, so for carbon number 6 in this case, so that's the indication it's a D sugar. So it turns out that D sugar is way more common for you to see because largely living organisms only have D sugars. We don't have L sugars. So we might, on paper here, and in the course of this chapter, have you write both D and L sugars, but in living organisms, almost exclusively D sugars. So all the way from, prokaryotes to eukaryotes and everything in between. All right. All right, so moving over to carbon number 1 now. So carbon number 1, in the open chain form, that is an aldehyde in this case for our aldose sugar. So it is not a chiral center. But when you do the nucleophilic attack here, kick these pi electrons out to the oxygen, and it's going to get protonated to become an OH. And the question is, where's that OH going to be? Well, it's got one of a couple of different options. So on carbon number 1, it originally isn't a chiral center in the open chain form. It is now going to be a chiral center. And depending on if you attack it from the front face or the back face, you get two possible different versions, the R and the S. But we typically aren't going to use R and S a whole lot here. We'll actually use two different terms, alpha and beta, instead. So this carbonyl carbon that becomes a chiral center in the cyclic hemiacetal form, we call the anomeric carbon. Let's cool. And again, that's this guy right here, carbon number 1. In fact, I don't want that arrow there, so we're going to take that back out. But that's him. He's the anomeric carbon. And again, in principle, you could form either of these two different forms. So I have the option of having that OH point down and the H point up, or I could have the OH point up and the H point down. Now, here's the deal. So we come up with two different names, alpha and beta, depending on what chirality that cyclic form is going to have at that anomeric carbon. And this is only for the anomeric that we assign alpha and beta. It's the only carbon where we had an option of either one being possible upon cyclization. So for the others, they're not involved in part of this cyclization process, and whatever they were in the open chain form, they're going to have the same chirality on the cyclic form as well. But at that anomeric carbon, it's that new chiral center we're forming that could form either way. Now it turns out if that OH is trans to the CH2OH group here, that's what actually gives it the designation alpha. So when they're trans, it's alpha. Well, again, you're much more likely to see D sugars than L sugars, like significantly more likely, like in terms like you may never even see an L sugar showing up. But technically, I want to give you the technical definition for alpha. It's when the hydroxyl group and that CH2OH group are trans to each other. Notice one points up, one points down. That's alpha. However, because you're most likely going to see this in the context of D sugars, either in this organic chemistry set or in biochemistry later on. So it turns out there's another thing, another way to memorize it based on looking at it specifically for a D sugar. For a D sugar, so you can think of the hydroxyl group is going to point down. For a D sugar, that CH2OH group is always going to point up. And if the OH points down, then that would be alpha. And so I like to think of it, alpha, the fish symbol, is when the hydroxyl group is down with the fishies. And that's alpha. Whereas if the hydroxyl group had been on the other side, where the hydroxyl group had pointed up and the hydrogen pointing down, that would have been beta instead. And again, this idea that if the hydroxyl group points down, that's alpha. Well, for D sugars, that's true. For L sugars, it's not true. But if the hydroxyl group and the CH2OH group are trans to each other, that's alpha. If they're cis to each other, that would have been beta. And technically, both forms will form in solution. All right, now what about if we take a look at the cyclohexane chair conformation version of this? So I say cyclohexane, but obviously we've got an oxygen in the ring here, so it's not pure cyclohexane in this case, but it works in principle the same way. And let's number those carbons around one more time. Numbers around the same way, so 1, 2, 3, 4, and 5. And in this case, going back around, so on carbon 2, again, we had an OH pointing off to the right. So, and right here is going to point down. So that's that guy right there. On carbon 3, it was pointing to the left, so that's going to point up. Carbon 4, again, is on the right, so that's down. So notice these are all in equatorial positions. And then finally on carbon 5 again is bonded to the oxygen that's in the ring. It's not going to have an OH group, but again, it has the CH2OH group, which once again, we want to point up, reflecting that this was a D sugar. So, and that also is going to be in an equatorial position. And that gives us carbon number 6 as well. All right, finally, we've got the anomeric carbon, carbon number 1 again. So we have an option, again, alpha or beta. So in this case, alpha is going to be down, but that happens to be an axial position rather than an equatorial. So, but these would be equivalent structures. And again, the whole up-down thing carries through whether you're drawing the Haworth projection or the chair conformation, either way. All right, so now I want to go back to our pyranose ring here. So, and again, we're going to get this equilibrium between the open chain form and the two different forms here. Notice the alpha with the OH pointing down, trans with the CH2OH group, or the beta with the OH pointing up, cis to the CH2OH group. In this case, there's this equilibrium that's going to be present in solution. Well, the majority of it is going to be in the alpha and beta cyclic hemiacetal forms, not in the open chain. In fact, very little, probably less than 1% would be in this open chain form in solution. We call the alpha D-glucose or alpha D-glucopyranose and the beta D-glucose or beta D-glucopyranose. These are referred to as anomers. So, and let's say you were able to somehow isolate, and crystallize just alpha D-glucose. Well, the moment you put that in solution, though, this equilibration is going to happen. So, and we call this equilibration process mutarotation. So you can have pure alpha D-glucose or pure beta D-glucose, but the moment it goes into solution, so you're going to get this mutarotation taking place, this equilibrium through the open chain form happening, and you're no longer going to have a pure anomer. You're going to have that mixture of the two different anomers. Now we said when they cyclize, 5- and 6-membered rings are the most common. We saw 6-membered rings, we call those pyranoses. 5-membered rings we call furanoses. Notice those 5-membered rings, you got 1 oxygen and then 4 carbons. So in this case, this is what happens with fructose. It forms a furanose ring. Now, turns out it can also form a 6-membered ring if the oxygen down here at the terminus, on the terminus carbon would actually do the cyclization process, and that actually is totally relevant. In fact, the 6-membered rings are more stable. However, forming these 5-membered rings gives us the biologically relevant cyclic form. So when you see fructose drawn out in any kind of biochemistry context, it's going to be this version that's drawn out. It turns out if you just put it in a test tube, this may not be the most abundant form, but it is the most biologically relevant and maybe the most common form to be formed inside the cell. All right, if you were going to number this thing, you kind of look at how we'd recognize the number here. So we've got carbon number 1. Oh, let's do that in red, actually. So we got carbon number 1, 2, 3, 4, 5, and 6. So going back over here, notice it's carbon number 2 that had the oxygen. That's going to become the new chiral center. So that's carbon number 2. So in a cyclic form, that's how you recognize that this is no longer coming from an aldose sugar, but from a ketose sugar, where your anomeric carbon, the one with the new chiral center, so that anomeric carbon is going to be not at the end of the chain. It's not going to be carbon number 1. Notice carbon number 1 is there, and then 3, 4, 5, and 6. And so when your anomeric carbon's at carbon 2 rather than carbon 1, so again, that's evidence you got a ketose. Now, it's easy to recognize, when I've got it drawn up next to the open chain form, which is the anomeric carbon. So, but how do you just kind of, recognize where the anomeric carbon is on a structure like this? Well, what you want to do is look on either side of the oxygen in the ring. So if you look at those two carbons, Whichever one of those two carbons is bonded to an additional oxygen atom, that's the anomeric carbon. And that's this one on the right. It's bonded not only to the oxygen in the ring, but the oxygen down here as well. Notice that's not true for carbon number 5. So in addition to the oxygen, it's just bonded to a carbon up there and a carbon down there, carbons 4 and 6. It's not bonded to an additional oxygen. That's the hallmark of that hemiacetal. You might recall, so back from some of the chemistry we did before, in the aldehyde chapter, if you react this with some sort of alcohol, with a little bit of acid or base catalyst, so all of a sudden you're going to end up with so that guy right there is your hemiacetal. So where you've got a carbon bonded to two oxygens, one's an OR and looks like kind of like an ether, and one's an OH, looks like a hydroxy group. The truth is, again, this is not really an ether or an alcohol, it is a hemiacetal. And that's what we've got going on here is this cyclic hemiacetal. And the way you recognize that anomeric carbon then is find the hemiacetal carbon. And that is the carbon that's going to be bonded to two oxygen atoms again. One of them is an OR, and the OR is part of the ring. And then the other one's going to be that OH, and that's your anomeric carbon. Now that's going to wrap up this lesson on the classification of monosaccharides. And in the next lesson, we'll talk about the reactions of monosaccharides. Now, if you found this one helpful, help me out with that YouTube algorithm and a like and a comment down below. Best things you can do to make sure this gets out to a broad audience. Now, if you're looking for the study guides that go with this lesson, if you're looking for a bunch of organic chemistry practice, take a look at my Organic Chemistry Master course. I'll leave a link in the description below. And if you're studying for finals in that Organic Chemistry Master course, there is a final exam rapid review where I cover all of OChem 1 in about 6 hours and all of OChem 2 in about 6 hours, and there are practice final exams that are part of it as well. I also have a course that's specially designed to help you review for the ACS standardized final, and I'll leave a link for that course in the description below as well. Happy studying.